Hey, hello everyone. A warm welcome to everyone on my course, which is called Building Real-Time Search Engine Using Apache Storm. So in this particular course, we will learn fundamentals about Apache Storm. I'm not assuming that any one of our learners or students have a prerequisite of Apache Storm. Just a little basic knowledge of Java is good enough. Then we will go into the basics of Storm architecture. We will cover high-level concepts, and we will also go in a little bit lower level just to understand at a logical level how the Storm is organized. Then we will build a Storm topology. So we'll start with a simple one, and we will progress towards a little bit more complicated one. I always believe that unless you apply the knowledge to real-life use cases, the idea does not register in the mind. So we will also use our knowledge to build a real-time search engine using and I will walk you through the code of the real-time search engine. We will also build a trending hashtag generator which shows the real power of how you can aggregate the data using the Storm in real time. And then we will also build a real-time web application by leveraging the Storm topology that we have built earlier for real-time search engine as well as trending hashtag generator. So what is Apache Storm? So Apache Storm is basically, it's a real-time stream processing engine. So what is a stream here? A stream is nothing but an unbounded sequence of tuples or just an array of objects. For example, an example could be, let's say if you are connecting to a Twitter to extract data only for a specific topics, you will basically register a webhook and you will start receiving the data right from Twitter in real time. That is a stream. Another example could be, let's say you are building an application where you are monitoring the check-ins in a restaurants just to see the restaurant popularity. You might use a Facebook or a Foursquare API. Again, you will get a Firehose which you need to register, and you will start getting this data into a webhook, which is like a web service that you have built. So you will get the check-ins as and when they happen in real time, and you can process the data in real time to see which restaurants are most popular, right? So those are some of the use cases that are useful to build the to use the Storm. And Storm is very useful to manipulate the data, to process the data in real time. It can do aggregations in real time as and when data comes in. So Storm is like a processor for real time as Hadoop, similar to what Hadoop is like for batch processing. Okay, so for real time processing we use Apache Storm. So we can process data as and when it comes in instantly, and it can react to the data instantly in a matter of few milliseconds or seconds. Then it's distributed, like you can scale your Storm cluster. Just like Hadoop cluster, you can create a Storm cluster with multiple nodes, and you can scale the system horizontally. It is also fault tolerant. If it could not process the message, it can send to you back an acknowledgement saying that it's failed to process the message, so that this cluster can retry the message. So it has those fault tolerant mechanism that is built in. It's an open source. It's free to use. And it was developed by Twitter in 2011, mainly to process its logs and doing a real-time analytics. And it's very popular these days, and it's used by a lot of companies. So here are some of the companies where Storm is used. So Twitter is using it for personalization, revenue optimization, and for search use cases. So Twitter is, as you know, it's a microblogging social network. Spotify, which is a music streaming service, it uses Storm to generate music recommendations, monitoring and analytics, monitoring and generating analytics in real time, and also targeting specific ads. WebMD, which is the web portal for medical professionals, it uses Storm to monitor the real-time Twitters on medical topics and provide real-time updates to medical professionals. Flipboard, which is a very popular social magazine, it uses Apache Storm for real-time analytics and also for search. Then Yahoo Japan uses Storm to analyze the feed contents, to monitor the systems, to detect some of the trending topics and crawl on websites. It uses Storm for doing all those operations. Okay, so as you can see, it's very popular distributed fault tolerant real-time processor system. So here is a high level architecture of Storm. So these are basically the various kind of nodes and the daemons running on those nodes. So at a high level you have basically a master node, and the master node, there's only one master node in the whole Storm cluster, and the master node runs a daemon called Nimbus, which is shown on the left here, right? So this is the daemon it runs, and Nimbus is responsible for delegating the task to workers. Okay, then on the right side you see the worker nodes. So on the worker nodes you also call the executors. On those executors you run a worker process called supervisor. The supervisor is responsible to understand the messages sent by Nimbus, and it will start processing the messages based on the topology that has been created. There could be multiple instances of executors. Then the coordination between the Nimbus and the executor is done by Zookeeper, right? So both this Nimbus and executor are stateless. So they keep sending their states to Zookeeper. That's it. And Zookeeper maintains the state, and Zookeeper helps Nimbus coordinate the task among all the executors, right? So if the executors go down or if the Nimbus goes down, state is not lost. If you just bring back Nimbus and executor back up, Zookeeper can continue to operate and maintain the state. The state is maintained in the Zookeeper special file. So Zookeeper just helps coordinate between Nimbus and executors. So inside all supervisor nodes, we run basically two types of processes. One is called spout and the other one is called bolt, and they operate like a direct acyclic graph structure where the data is processed from left to right, and there could be forks, there could be parallel nodes in between, but there are no cycles in the graph. So on the left you have a spout, which is nothing but a source of stream. So here, for example, if you are building a Twitter processor network, you write a code that can connect to Twitter and start getting the data. So spout just acts as a source of the stream. Then you can configure to process the data emitted by spout by multiple bolts. So spout can emit the data, and the topology will dictate it can goes to one or more bolt, and each bolt can do a specific processing. For example, let's say if you're building a word counter application, a spout can just read the data from a file or a database of all the lines, and then it can split the lines, and then the bolt can be responsible for counting the words, and you can have multiple search words. Then these bolt again can process the data and again send it for other set of bolts for doing additional processing. So each task we can divide into multiple bolts so that parallelism can be built in, and the data can be emitted to other bolts for processing. For example, if you're building a word counter application, you can have one bolt for doing the splitting of sentence into word, another bolt for doing the word counting, and then last bolt for doing aggregation and sorting the data. So each of these tasks can be done by a bolt, and we can build multiple bolts in parallel, and that's where the efficiency and the real-time processing comes into picture. All of these operations, right from spout at the left to the bolt on the right, this can happen in a matter of milliseconds, and you can scale it horizontally by adding as many bolts as you need. And you can have multiple of such spouts and multiple such configuration. So each of the configuration where you have spout, bolts, and another bolt, it's called a topology. So here in this particular diagram, I'm showing you two topologies, one on top and the other one is on the bottom, and you can build as many topologies as you would like in a given Storm cluster. So here is an example topology which dictates how a spout is connected to a bolt, giving a word counter example. So you have a file spout which is reading a data from the file, which is nothing but the text data line by line. Then the file spout topology will dictate how the file spout is connected to the next bolt. Here we are connecting this to a sentence splitter bolt, which is responsible for splitting the sentence into multiple words. And the sentence splitter bolt is then, topology says, hey, sentence splitter bolt, you send the data to word counter bolts, and there are multiple such bolts. So sentence splitter can send few words to the bolt on the top and a few words to bolt on the bottom. So each word counter will count the number of words and it maintains the count internally inside a dictionary. And then it can, since there are multiple bolts, there is an efficiency are gained, and each of those counters are operating on a different words. Then at the end there is a final bolt which can do the word sorting and do a descending order sort, so that it can show which are the most popular words in this particular file. So this entire configuration, which dictates how spouts are connected to bolts, is maintained in something called a topology. Okay, so and there are different ways of doing a grouping between a spout and a bolt. One way of grouping is called shuffle grouping, where the shuffle grouping says, hey, each of the data that we get from spout, send it to the next bolt in a random order. Okay, so from first, and that should be okay for cases where you are sending an entire object to the next bolt. For example, here file spout is sending an entire sentence to a splitter bolt, so it can do a random shuffling. Now from sentence to word counter we cannot use random shuffling, because each of the word counter bolt is doing processing only specific words, right? For example, if I have a word called dog, then whenever, and if there are multiple sentences that involves dog, this sentence splitter needs to ensure that all the dog words, it sends only to the upper word counter. And let's say there's another word called cat, all the words called cat, it should be sending to the lower counter bolt, because then that means each of the word counter bolt will perform accurately word count only a specific word. This is achieved by using something called a field grouping between the sentence splitter bolt and the word counter bolt. This field counting grouping, you can specify that it can do the field grouping by word, which means only word so it can do the grouping by the word. So if initially the sentence splitter bolt has sent the word to dog to the top counter and cat to the bottom counter, all subsequent dog words will always be sent to the top bolt, and all the words with cat will always send to the bottom bolt. That way we ensure that the specific words are always sent to the respective bolts, and that is achieved by using field grouping. Again, between the word counter bolts and the final word sort bolt, the grouping can be shuffling. So these are the two examples that I gave you, like shuffling grouping and field grouping. There are several other grouping that you can use. You can refer to the Apache Storm documentation by going to a website called storm.apache.org. But these are the most popular ones that are used. So this is a good introduction of Apache Storm so far, and we can start diving into a little bit deep and start looking at the code.